Alright guys, as mentioned yesterday, I'm going to be going through a pretty special function and I'm going to be looking at differentiation by first principles. So the first thing we want to be going through is functions and just what happens when you input things into them. So all of these are functions. So we use lowercase f for a function, so this means that given x, this function outputs x squared. So an example would be given 2, my output here is 2 squared, which is 4. Given f of 0, if I put 0 in, my output is 0 squared, which is 0. What I want you to think about is, once if I give it f of, say, 2 plus 3. So have a think about what that might be. Well, that's just f of 5, which would be 20, which would be 25, wouldn't it? So what doesn't happen is this: f of 2 plus 3, it's not equal to 2 squared plus 3 squared, is it? Because that's 4 and 9, it's 13. So that's not true. So if I say give me f of, say, a plus 1, you can't just put a in, square it, and then add 1. This would actually be equal to a plus 1 squared. So the idea is whatever I put in, I have to put that in for the variable in the equation. So let's have a look at this one. F of 0 is 4. So this is just a straight line 4. No matter what I put in, I've just got a constant output. F of 10 is also 4. So it has a constant output, no matter the input. Here, if I went f of 0, I get 0, because sine of 0 is 0. If I put f of pi in, right, you could, same on a calculator, that would be sine and put pi in, right? And my calculator's in the wrong mode. I'd also get 0, right? And if I went f of pi over 2, all right, that's sine of pi over 2. And so if I was to put it in as a function, I would get 1, okay? So these are all functions. So one last example, f of, let's say, 2, well, that's equal to 3 times 2 squared, because x is now 2, plus 2 times x is 2, so it's 2 times 2, and then plus 1. So what have I got? I've got 12 plus 4 plus 1, so I get 17. So if I put 2 into that quadratic, I'd get 17 out. And that is how those functions all work with inputs and outputs. But just notice that that's not true. It works more like that. And we need to know that for this next step. So what I've got is I've got some random function. It's just f of x. So on this axis is output, and on this axis is input. So let's take a point x, all right? Then this point here, well, that corresponds to f of x. And so what we're going to be doing today is we are going to be approximating the gradient of that function. So calculus, it's all about how things change. Calculus is all about things that change in the world. So the weather is just a big calculus problem, because it's all just about how things change. Given initial data, how do things change, and how can we predict the future? So if we were to give this function x, our output would be f of x. And so I want to approximate that gradient. So some of you might have seen this before. I can approximate the gradient by taking the tangent. So if I take this point and let's go a little bit lower, and this point here, well, that's not a bad approximation of the gradient here, is it? But what do I need to do? I need to bring this point closer and closer, right? So the closer I bring this point, if I came to here, it's getting up to be a better approximation. If I had a point like really close to that, my approximation gets better and better. And then when I'm pretty much on that point, right, I've got a tangent, because you can't have a gradient of a line without some incremental change, can you? You can't technically get the gradient at a single point. So what we need to do is we need to take a different point. So we'll take this point, and let's say it's h away. So let's say that this is h from there to there, some change. So then this point here becomes x plus h, because we've got x, add h to it, we get x plus h. And so what's the output going to be here? If we go across, this point here is going to be f of x plus h. That's my input, and so that's going to be my entire output. And so what we want to do is we want to take the tangent of this. Like, we want to take the line through this point. So what is the gradient? I'll do it in red. What is the gradient of that line? So I'll just head that up. Gradient of red line. Well, that's going to be equal to rise over run. Okay, well, that's pretty simple, right? What's the rise going to be? Well, the rise is going to be the large point, the bigger point or the higher point, take away the lower point. So that's going to be f of x plus h, take away this point that's at the bottom, f of x. That's just your change in y. That's just this height, isn't it? This point, take away this point, gives you that distance, our rise. And what is our change in x? Well, it's going to be the same thing. This point, take away this point, but we've already defined the change in x. It is just h. So the gradient of this line is going to be f of x plus h, take away f of x, all divided by h. Well, that's all well and good, but you're probably wondering why we're doing this. Well, let's make h get smaller and smaller and smaller until it's pretty much zero. And what do you think is going to happen to this function? And hopefully you're thinking to yourself, well, that reminds me a lot of that last lesson we did on limits. So what we're going to be defining is the gradient. So let's take the gradient function. Let's say the gradient function. So when we take the gradient function, we need new notation. We've got f of x, but we want to know the function that tells us the gradient. So the gradient at this point, let's go f prime at x. So this is from year 12. The derivative, or the gradient function, is equal to the limit as h goes to 0 of this function here. That is differentiation by first principles. So as h gets smaller and smaller, this line, this red line, gets shorter and shorter. So it would come to here, and then would come to here, and then get to here. And as this line as h gets shorter and shorter, we get a very accurate gradient at that point. But it doesn't have to be at a single point. We can get this for any point on the line by taking a very small change in change in y over a very small change in x, and we'll get the gradient at that point. So let's have a look at what this looks like. We need to look at an example. So I'm going to rewrite this down up here on this new piece of paper. So the gradient function, f prime of x, is equal to the limit as h tends to 0 of f of x plus h minus f of x all over h. The change in y over the change in x for any point x is given to us by this formula. And this is where you're going to need to have some good algebra. So let's have a look at f of x equals x squared minus 5. I want to find the derivative of this using first principles. So what is the derivative by first principles? So f prime of x is equal to the limit as h gets closer and closer to 0 of the function defined at x plus h. And so remember from that first piece of paper we did, I gave you an example what happens when we put two variables, or even a variable and a constant in, to an x squared. So we have to put x plus h into this. So it's going to be x plus h squared minus 5. That's just f of x plus h. Now take away f of x. So take away x squared, and if you take away negative 5, you add 5 all over, and it's only h on the bottom. So here we have, where's my red pen? Those two are the same, and in blue we have that. So there's f of x plus h, because negative 5, remember, isn't affected by the input, it's just a constant. And then we're taking away f of x. So what's the top going to become now? Because you'll be wondering, well, you can't divide by 0, and you're right, so we need to manipulate this. And we did a problem very similar to this in the last lesson. So the limit as h goes to 0, expand and simplify the top. Well, that's going to be x squared plus 2xh, or hx, minus 5 minus x squared plus 5. And you'll notice that there's going to be quite a bit of cancelling down. X squared, take away x squared, minus 5 plus 5. And now we have the limit as h tends to 0 of 2xh over h. And the h's cancel as well. And so we've got the limit as h goes to 0 of 2x, and that's just equal to 2x. As h vanishes, we would just be left with 2x. Okay. Let's have a look at one more example for today. So I'll do it on the back of this piece of paper. We know that the gradient function is just rise over run, and let's have a look at what happens as we let the run get smaller and smaller. Let's bring that tangent line down so we get a tangent at that point. So let's just go a little bit above that point and a little bit to the right of that point, and now make that smaller and smaller. What's going to happen at that point? And let's have a look at it for this really gnarly function, 3x squared plus 2x plus 4. Okay, this is going to be quite a bit of algebra. It's going to get pretty big pretty quickly, but we're going to have x plus h in here. So this is going to be f prime of x is going to be 3 times x plus h squared. So I'm just replacing x with x plus h for this first part, plus 2 x plus h plus 4. So that's only doing this first part. Now let's take away f of x. So take away the original function pretty much. So take away 3x squared, take away 2x, and take away 4. That is the entire top part done now. So this part here is this bit, and this part here is this bit. So you'll notice I'm doing the take away in one step. I could bracket that off and have the whole thing with addition, but I just try to save myself a step and some room. And this is all over h. And I need to remember I'm taking a limit as h goes to 0. That's important. So this is going to be equal to the limit as h goes to 0. And now I'm going to expand this whole thing. So that's 3x squared plus 6xh plus 3h squared plus 2x plus 2h plus 4. And now I'm taking away all of this stuff. And this is all over h. So like I said, it's getting big and gnarly pretty quick, right? Well, this usually happens as things cancel down relatively quickly. We have 3x squared take away 3x squared is 0. We have 2x take away 2x is 0. We have 4 take away 4 is 0. And so what are we left with? We are left with 6xh plus 3h squared plus 2h. That's all we're left with. So the limit as h goes to 0 of 6xh plus 3h squared plus 2h all over h. Well, we got a little bit more cancelling to do, and h can cancel in every single one of those terms. We're now taking the limit as h goes to 0 of 6x plus 3h plus 2. Now what happens to this function as h gets closer and closer to 0? Well, as we get closer and closer to 0, this here would vanish. It would get closer and closer to 0 as well. And so this is going to be equal to 6x plus 2. And there we have it. We have found as h goes to 0, our function goes to 6x plus 2. So this is going to be today's lesson. Pretty much done. But I want you also to think about, is there a quicker way to get from this function to this function? So this function tells me what the gradient is at any point, and this function is the original function. So if I want to know the gradient at 0, well, at 0, this thing has a gradient of 2, because f prime of 0 is 2. So that's where we're going forward from now. But you're going to spend a day or two doing a few of these by first principles, and we'll leave it at that. Hit me up with any questions, like that smash button.